Okay, folks. I now want to take a moment to review some trigonometry. Okay. So I'll try and review all pre-calculus in 10 minutes. I won't make it. I absolutely expect you to know the entire unit circle. I know that at some point somebody showed it to you, okay? And maybe you learned enough of it to get through, but you absolutely need to know the entire unit circle, okay? So the first thing I want to say is with the unit circle, you need to know two things on it. You need to know all of the special angles that show up on the unit circle, and you need to know the ordered pairs of each point on the unit circle. Okay? To learn the angles of the unit circle, all of them are angles of pi over 12. People don't always realize that. They're all pi's over 12. What I do is I take and divide, so remember this is the angle pi here, and so then I break the top part into twelfths. I don't write these as part of my unit circle because 1 pi over 12 isn't a helpful unit circle angle, okay? But I would do that and I'd have a total of 12 of them, and then if I go all the way around, I've got a total of 24. So I guess you could also say I'm dividing this into 24 sections, but it's 12 in the top, 12 in the bottom, okay? So I won't ever put these tick marks on a unit circle, and I'll erase them here in just a second, but let's just run through it. This is 1 pi over 12, so then what would this be? 2 pi over 12, but 2 pi over 12 reduces down to pi over 6, right? And this is 3 pi over 12, which reduces down to, everyone tracking with that? Okay. This would be 4 pi over 12. Okay, so I'll write that one. That's 4 pi over 12, but again, that reduces down to pi over 3 when you simplify it. Okay, I won't write 5 pi over 12. This is 6 pi over 12, but that's really the angle pi over 2. Okay, so for example, if I point to this angle right here, I need you to know that this angle right here is 5 pi over 4. There are some patterns that you can observe in this. First of all, notice that this is called the unit circle. It's called the unit circle because the radius of this circle is what? It's 1. The radius of this circle is 1. So this ordered pair right here is the ordered pair 1, 0, right? This would be the ordered pair 0, 1, right? So anyway, what I want you to notice is that the angles that are closest to the x-axis, not on the x-axis, but closest to the x-axis, are your pi's over 6's. So this is pi over 6. This is just a little bit less than a full pi, so 5 pi over 6. This would be 7 pi over 6, and then this would be 11 pi over 6. Okay? If you can't remember that, you could count all your 12s, but that'll take you way too long, and you definitely can't do that on an exam. You've run out of time. Okay. Notice also that your pi's over 3's are closest to the y-axis. So this is this is pi over 3. This would be 2 pi over 3. Down here I would have 5 pi over 3. I feel like I did that wrong. 4 pi over 3. And then 5 pi over 3. It's just a little bit too zoomed in. So notice, so again, what I'm saying is your pi's over 6's are closest to the x-axis, your pi's over 3's are closer to the y-axis, and then who's in the middle? All of your pi's over 4. Okay. Any questions on that? So of the things you need to know, be able to do very quickly, that is step 0. Okay, know all of the angles on your unit circle. Okay. Now, for each one of these that I've marked on here, you need to know the ordered pairs. Okay? I've already listed, oh, let's just say this. I didn't say this. This is the angle 0, which is the same as 2 pi, which is the same as 4 pi, 6 pi, etc., right? Okay? I already labeled that as pi. It's also minus 1 pi, minus 3 pi. It's all the odd multiples of pi. But you have some points that are very easy to spot on the unit circle, and sometimes people forget about them. Okay? So the pi's over 2's and the pi's are the easiest ones to find the ordered pairs for. So just go on the fact that it is a unit circle, and we're talking about the xy axis. Okay. This next step is how I learned the unit circle. I don't know if it's the best way, but it's the way I teach it because it's the way I learned it. Okay. I have 3 little phrases that I've memorized. Okay. So I'm gonna let me zoom out. It's too big. Let's go to 100. Okay. So the 3 phrases that I've memorized is that a lot is equal to the square root of 3 over 2. Okay, so I tell myself a lot is the square root of 3 over 2. Same is the square root of 2 over 2, and a little is 1/2. Okay? Notice that all 3 of these are fractions over 2. And in fact, there's even more of a pattern if you remember that 1 is the same as the square root of 1. So it goes going from the lowest up, square root of 1, square root of 2, square root of 3. Absolutely, got to know those.
Is there an actual square root of 1 though?
Yeah, it's what number times itself gives you 1. Yeah, so we don't write the square root of 1, but there is a pattern happening there. So that helps you remember what's going on. Yeah, great question. So this is how I find my ordered pairs on the unit circle. Let's suppose I was interested in this point right here. Okay? And I'll let you decide how cluttered you want your diagram to get. Okay? So what I will do is I'm going to draw a triangle to that point. Okay? So if I start at the center, how do I get from here to here? Well, I'm going to go along the x-axis. How far am I going to go along the x-axis? I'm going to go a lot. Then what am I going to do? I'm going to go up the y-axis. How far am I going to go up the y-axis? A little. So what is this ordered pair right here? It's the square root of 3 over 2, comma, 1/2. Okay? Let me do another one. Okay? So I'm going to draw this triangle right here. Okay. And again, at this point, I'll let you decide how cluttered you want this to get. Okay. I made it kind of big, but maybe not big enough. Okay, so how did I get from the center, from the origin, to this point? Well, I'm going to go out the same distance that I go up. So I'm going to call this the square root of 2 over 2, comma, square root of 2 over 2, because it's same, but now I got to be careful of the sign, S-I-G-N. Okay? I got to be careful of the sign, because I didn't go to the right the same distance, I went to the left. So what sign goes in front of this? A minus sign, but the y value is still positive. Okay? Let's do another one. Let's just do this one right here. Okay. How did I get here? I went back a little, and then I went down a lot. Okay. All right. By the way, if I did this one right here, you don't really draw a triangle. It's hard to see a triangle because it's a 180-degree triangle. Okay. But then again, finding the coordinates there is straightforward because it's -1, comma 0. So you don't need my little gimmick to get there. Yeah, Karina.
Also, the way that helps me remember is as long as you remember all the points on like pi and pi over 2, and, So it's either 0 or 1 or 1 or 0, so it's either increasing or decreasing. So at the beginning it's 0 or 1 for 0 degrees, and then for 90 degrees it's 1, 0. So between those two, cosine is going from 0 to 1, so then it's 1/2 root 2 over 2, root 3 over 2, and then sine is doing the opposite.
Good,
So
that's
it's
helpful.
Growing or decreasing.
Yeah, so what Karina said here is that if I put this order pair up, I've got radical 2 over 2, radical 2 over 2, and if I put this one here, I'd have 1/2 comma square root of 3 over 2. So notice how these are laddering, the x coordinates are laddering down, radical 3 over 2, radical 2 over 2, 1 over 2, whereas the y coordinates are laddering up, 1/2, radical 2 over 2, radical 3 over 2. Okay, so there's a nice pattern there. There's lots of patterns in this. That's where all your trig identities come from, all the patterns in this. Okay. So anyway, I need you to be able to identify those coordinates lickety-split. Okay, that's step 1. Okay. So step 0 is make sure you can do all the angles. Step 1 is make sure you can do all of the ordered pairs on the unit circle. Okay. Step 2 is knowing how do you get actual trig values from this. Okay. So the sine of the angle theta we've memorized is the opposite over the hypotenuse, correct?
Sure.
Okay. Well, first of all, what is always my opposite? Or what is always my hypotenuse on the unit circle? Always on the unit circle, my hypotenuse is 1. So we don't even really think about it on the unit circle. Okay? Then let's say I was thinking about this blue triangle right here. Well, this is my angle, right? There's my theta. So my hypotenuse is 1, this length right here. And then what is the length of my opposite? It is simply the what coordinate? The y coordinate. Notice the y coordinate tells me the height of this triangle. So this is y over 1. Okay? And in fact, we'll always just say that on the unit circle, if I want the sine of the angle, I just take the y value. Okay? The cosine of the angle is just then the x value by the same argument. It's actually the adjacent over the hypotenuse, but the length of the adjacent is simply your x coordinate, and the hypotenuse is 1. Okay? So step 2 is being able to find the sine and cosine for any angle. Step 3 is answer the question, depending on what the question is. Okay? So let's work a couple of these together here. So let's go ahead and find the sine of pi over 3. Now, I don't think you should draw out an entire unit circle for your test. I feel like that takes a chunk of time. If you want to do that, that's fine. I've had some students in my other class request that I put a circle with a xy coordinate system on it. That's fine, but that's all I'll put. I won't put any tick marks. I won't put any other information on it. I do not recommend filling it out and then taking it around with you from problem to problem. But that might be what you find is best, so I'll let you decide. Okay, but let me show you how I would find the sine of pi over 3 if I were in a hurry on a test. Okay, if I want the sine of pi over 3, I would just quickly draw the angle that I said you had to know, which isn't that angle. It's a little more extreme. It's this angle right here, right? Okay, then I would say, well, how did I get there? Well, I went out a little and then up a lot. There are the coordinates. Notice I didn't draw the whole unit circle to answer this question. I drew a tiny little triangle that matched the angle, and then I labeled it by its coordinates of how I got there. Then, for the sine of pi over 3, I simply want the y coordinate. So the y coordinate is the square root of 3 over 2. Okay? Let's do a different one. Let's do... what's interesting on here? Let's do the tangent of minus 3 pi over 4. Okay. First of all, minus 3 pi over 4, let's see, that's 1 pi over 4, 2 pi over 4. Minus 3 pi over 4 is over here. Okay. You don't have to draw the angle. I mean, this is the angle. Oops, sorry, that's not the angle because we're doing minus. This is the angle, but the triangle that I quickly form looks like this. How did I get there? I went back the same amount that I went down. So the coordinates here are minus the square root of 2 over 2, comma, minus the square root of 2 over 2. Okay? At this point, I recognize the answer as 1. Actually, I knew it was 1 a while ago. But let's run through this a little bit more slowly. Okay? So when I said, step 2 is find the coordinates and step 2 is find the sine and cosine, we have to answer this question, which is about the tangent. Well, we remember that the tangent of an angle is the same as the sine of the angle divided by the cosine of the angle, which is simply my y coordinate, because we said the y was the sine, over my x coordinate, which is what we said the cosine was. Well, what was the y coordinate? It is minus square root of 2 over 2. What is the x? Sorry, I did that wrong. I pointed at the wrong one. It's this one right here. That's the y coordinate. And then what is the x coordinate? It's this coordinate right here. So that's, we'll do that in green, minus square root of 2 over 2. But here I see, oh, those cancel each other out. And so what is the tangent of that angle? It's 1. Okay? You need to get down to the point where you can do that in about 15 seconds. Okay? Maybe faster. Okay? So I consider this like your multiplication tables, right? You got to have these facts down, and they are really just facts. But I've given you kind of a methodical way of coming up with them if you don't have them memorized. Because I don't think you could just look at the unit circle, memorize it, and have it be of use. You kind of have to understand it as a working document, something that you produce results from it. Okay? Yeah?
So what about like an easy trick for something like this, 400 pi over 3? What would be the...
I'd rather hold off on that. I'll let you think about it, but you have to decide how many times around the circle you went.
Right.
And so notice that around the circle is 6 pi, well, it's 2 pi, but it's 6 pi's over 3's.
Right.
So you would divide 400 pi by 6 and then look at the remainder of it.
Oh, and that would be the number of times.
That would, so 6 dividing by 6 would give you the number of full laps around, and then the remainder would show you where you end up at.
Cool.
Yep. Okay. Folks, here are some trig identities. These two will be readily tested on often. Okay? Readily assume that you know those. Okay? And I'm not getting into the other definitional ones. Like for example, I could add that the cosecant of theta is 1 over the sine of theta. I expect you to know those identities as well. The co-identities, the reciprocal identities. Okay? I won't readily test you on these, but I can find ways, with true-false questions, stuff like that. But I'll never give you I'll find the derivative of this problem, and you have to have used this identity to get through it. Okay? But I don't think it would hurt you to go ahead and just memorize them, the sum and difference formulas for sine and cosine. Okay? All right. I keep kicking the proof for this down the road. Okay, this was I think this was the second limit we put up on the board in this class. We said that this limit, we looked at a graph of it. We said that this limit was 1. Okay, it's shown up a few times. It was on your test. It showed up. Okay, unfortunately, we're still going to just assume the fact that it's 1. The proof is postponed one more time until chapter 4. Where we'll have a very easy way to prove it. Okay. If I get a chance, I will make a video for this so you can see where this limit comes from. But again, I guess I'm going to just have to ask you one more time to take it on faith. We're going to need that for the next page. Okay, the next thing we want to find is this limit right here. Okay, and I want to show you this because I think it uses a couple of slick limit tricks. Okay, so let me run through it. If we look at the limit as theta approaches 0 of the cosine of theta, minus 1 over theta. Okay. Well, I don't know much about this limit. I could look at its graph and take a guess or something like that. But I do know some things about limits involving sine, namely the previous page. So let's see if we can find a way to use that. Okay. So one thing I could do is if I could get something in terms of cosine squared, then I can often replace an expression with a sine, or sine squared, depending on how it falls out. So I'm going to go ahead and multiply this by cosine of theta plus 1 over the cosine of theta plus 1. I don't think it's readily apparent why we want a perfect square in that numerator for this problem. Okay? Unlike the other ones where you used the conjugate trick, we did that to help get rid of things outside of square roots. Right? I don't have any square roots in this problem, but it turns out that this is the appropriate trick for this problem. So this gives us the limit as theta approaches 0 of the cosine squared of theta minus 1 all over theta times cosine theta, cosine theta plus 1. Yes, plus 1. Okay. All right. So, I know from my Pythagorean identity on the previous page that the sine squared theta plus the cosine squared theta equals 1. If you can't remember that, that's fine. You want to remember it. You want to memorize it. But it's the Pythagorean identity. A squared plus b squared equals c squared. What's 1 squared? It's 1. So this is just the Pythagorean theorem. Okay? In fact, if you take on the unit circle and take what I told you about x and y being the sine and cosine, you would have this theorem, or this identity. Okay? So we know that sine squared theta plus cosine squared theta is equal to 1. I've got a cosine squared theta minus 1. So let's see here. If I subtract over a 1 onto this side, so it's starting to look like that, and take the sine squared over as minus sine squared theta, I think I'm ready to make a substitution. Okay? So this gives me in the numerator minus sine squared theta over theta times the cosine of theta plus 1. All right.
Quick question.
Yeah.
You just leave that theta chilling by itself, since it's theta times cosine theta.
Yeah.
I've never really
It's
seen
like
the theta
that.
chilling like that.
Well, it's like
the
the H.
or the x. It's whatever you put in for the angle.
Because I thought the cosine theta was like almost like the x.
Yeah, so this is a choice of variables, and that's all it is. So I could have used x's here, I could have used h's here, but
Okay.
Yeah.
I see what they're saying.
Mhm.
No worries.
okay. So what I'm gonna for my next move, so we've got something like a squared over b times c. That's kind of the structure of this problem. So for my next move, we're gonna say that's a times a over b times c, and then I'm gonna take a over b times a over c. So I'm gonna break up the fraction that way. Okay? So this gives me the limit as theta approaches 0 of the sine of theta over theta times minus the sine of theta all over cosine theta plus 1. So what did I do? Well, I brought one of these sine thetas and put it over theta, and I took the other minus sine theta and put it over this. Now again, I can only do that because what are all of the operations happening? I've got a sine of theta times a sine of theta, and I've got in the denominator this theta times cosine theta plus 1. So it does have this structure up here, and so I can break it up this way. It's a tough move. Okay. All right. So now I'm going to distribute the limit over the product. Can I always distribute a limit over a product? I'm doing it. Can I always do it?
No.
No, it's provided the underlying limits end up existing, right? So if either of these came out to not exist, then this move would be illegal, and I'd have to backtrack up to here. Okay? But it turns out they'll both exist. Okay? What is the limit of this first? What is this first limit?
1.
That's 1, right?
Good question. Could you have kept the negative on the sine
Yep.
theta over theta
Yep.
instead of the?
Yep. And then, but then I would probably then factor it out. The negative out, so then I would say that there's the negative that I factored out, and then 1 is what the limit evaluates to.
Okay.
Because so you asked a good question, but I just want to make sure I set this up to use the limit from the previous page, where we said the limit as theta approaches 0 of the sine of theta over theta. That limit
Oh, I see.
is
Yeah,
1.
yeah. Okay.
Okay. Great. Now this function right here is continuous, right? It's continuous everywhere it's defined, and it's only undefined when I get a 0 in the denominator, which happens when cosine of theta is minus 1, which only happens at my odd multiples of pi, right? Again, so you got to know this whole unit circle. When will the x values be minus 1? Only when I end up over here. Where is here? It's at pi, it's at 3 pi, it's at 5 pi, it's at minus pi, minus 3 pi, minus 5 pi, but certainly not at 0, which is our limiting value. So I can go ahead and evaluate this through direct substitution, and I get minus the sine of 0 over the cosine of 0 plus 1, which just gives me 1 times 0, which equals 0. Okay. Again, what's the cosine of 0? Cosine of 0 is 1. 1 plus 1 gave me 2 in the denominator. The sine of 0 is what?
0.
The sine of 0 is 0, which gave me the 0 in the numerator, which is why this whole thing is 0. Okay. Let's take a break. I've got 45, so let's start up here at 55. Okay, folks, I'd like to get back to it. Oh, was I going to say something else? Yeah, let me. So, picking up where we left off, we've derived 2 important limits that we're going to need in order to do the proof of the derivative of the sine function. Okay? So let's go ahead and find the derivative of the sine function. Here I say it will be the cosine of x. That's interesting. Okay? Let's see what happens here. So if I have f of x is equal to the sine of x, then f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. This is equal to the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. So typically, I've not asked you this limit problem before because it's a tough limit problem. Typically our goal is to somehow find a way to finagle this h out as a factor somehow, and then cancel it with this h down here. That's sort of the general strategy of these limit problems. But you can't do that in this case with these trig functions. There's no nice way to get an h out of there. Okay? So instead, we're going to try some of our trig identities. Okay? The first one I'm going to do is the limit of, or sorry, is the sum of two angles within a sine. Okay, so that's this identity right here. I'm going to go ahead and use this. Okay. So it turns out that the sine of the sum of two angles can be written as the sine of x times the cosine of h plus the cosine. Let me keep them this way. Plus the sine of h times the cosine of x. Okay? So all of that is what I just did with this expression right here using my sum of angles identities. Minus the sine of x, that's just that lingering one, all divided by h. So it's not clear that we've gotten anywhere closer, except notice that the x's are no longer attached to the h's, and in some ways that'll be beneficial. Okay. So let's give this a shot here. I'm going to go ahead and group, so I'm sure I've got this right. X, yeah. So if I had a fraction, it's up here so the viewers can see. If I had a plus b plus c over d, I could rewrite that as a plus c over d plus plus b over d. So I'm going to rewrite it to look like that. Okay, so I'm going to collect together this first and last term and put it over h, and put the middle term also over h, separate them by addition. Okay. By the way, folks, this is a handy tool. Kind of give yourself something that looks like your problem, but is stripped down, so you don't get bogged down by the variables and the confusing functions and such. And just say, what are my, because this is just fractions. What am I allowed to do with fractions? Okay. All right. So I'm going to group together the first and last term and put them over h. That gives me sine of x, cosine of h, minus sine of x over h. And then I'll go ahead and distribute the limit over those sums. So then that's the limit as h approaches 0 of the middle term all over h. Okay? How are we doing? This is an exercise in hanging on. I'm not going to ask you to do this on your own. Okay? Now, that said, there's a couple of slick tricks in here that I do often test with true or false type questions. And I'll show you kind of what I mean by that. But I would never ask you to go all the way through this proof. It's pretty messy. Okay? All right. So this is a slick trick. Okay? Notice that this factor right here, sine of x, and this factor right here, sine of x, I've got common factors. I could factor them out of the fraction. But I can take that one step further. We saw this in a previous problem. My limiting variable is h. So even though the sine of x in both those terms it's a variable as far as x is concerned, it's not a variable as far as h is concerned. So it's like a constant as far as h is concerned. So I can pull that factor out of the limit. So let's do so. That would give me the sine of x times the limit as h approaches 0 of the cosine of h minus 1 over h. So what did I do? I factored the sines of x's out of the fraction and then pulled them all the way out of the limit since they didn't depend on h. Plus, over here it's same but not quite as complicated. I've got a factor of cosine of x that does not depend on h, so let's factor it out. This gives me cosine of x times the limit as h approaches 0 of the sine of h over h. So folks, we're done. This is the sine of x times what? This limit look familiar? It's this limit right here, right? With h's instead of thetas, and that limit came out to be 0. Times 0. Plus the cosine of x times this limit here. What did this limit come out to be? Everybody, all together? 1. So we just get the cosine of x. Really interesting, folks. The derivative of the sine curve is the cosine curve. That's a connection that we were never able to make in a trigonometry class. That relationship between how the cosine curve changes and what the sine curve is doing. I want to jump into Desmos real quick. Okay. Calculus is a very visual subject, folks. I've got limited time to show you graphs and things. Okay. But on your own time, I think you should look at that. Okay. Let's say I have f of x is equal to the sine of x. Remember what we said about the derivative. We said wherever the function is increasing, the derivative is positive. Okay? And wherever the function, red here, is decreasing, the derivative will be negative. And wherever I have horizontal tangent lines on my original function, the derivative will touch 0. Right? So let's see. Where along here, if I were to draw little tangent lines, where along here, along this period, is the tangent line the steepest? It's a little hard to tell. In the middle, right? So here it's kind of leveled off. It's getting steeper, 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 and it starts leveling off again. Okay, that's a concept called concavity. Some of you have heard of it. We won't touch that for another unit. Okay? But anyway, where is it steepest? Right here at 0. That means that's where the derivative has its highest value. Now, as I approach, let's see here, this is pi over 2. As I approach pi over 2 with my derivative function, the original function is getting less steep, but it's still increasing. And it doesn't arrive at 0 until I get to pi over 2 for the derivative. So this is what this segment looks like. Notice that from pi over 2 onwards until I get to, where's this? This is at 3 pi over 2? No, that's a lie. That's a lie. This is at pi, sorry. Hey, no, I've got a mistake. Just a second, I can't erase this on here. Sorry, folks. This is pi here. This is 4 pi, 5. Oh my goodness, 3 pi over 2. That's what I said first, and I didn't trust myself. Sorry about that. Okay. Sorry about that, folks. That's 3 pi over 2. Okay. Notice between pi over 2 and 3 pi over 2, what is my function doing? Decreasing. So its derivative needs to be negative. And sure enough, it looks something like this with its maximum negative value, where this would have the maximum negative slope. Okay? Well, what curve am I sketching here? The cosine. So we see that the derivative of the sine curve is the what? The cosine curve. I've mentioned this before. One of the reasons why I like Desmos so much is, and it has its negatives, and notice I always check it after I've done something, not before, okay? Which you can check before, but I'm never assuming you're going to have Desmos on a test. But notice here I can just type f prime of x, and it sketches the derivative without me actually calculating the derivative, and that's kind of nice. Okay, it's just a time saver. Okay. Let me erase my mess. Okay. All right. Any questions on that? Yes, sir.
F2 prime goes back to being sine of x.
Great question. Well, no,
No.
not quite. Not quite. Okay. And we could check that. You could look at the second derivative and see that it doesn't overlay on top of the red function. Okay. But there is a relationship between what the cosine's doing and what the sine's doing, but not quite. Okay. Notice, for instance, let's see here. Notice, for instance, right here, the cosine curve is decreasing. But if we thought sine was its derivative, then sine would have to be negative there. So it's not quite. But there is a relationship. Let's jump to that now. Maybe. No, first we'll do this. So, I've mentioned this before. This is a hard part of this class. You've learned a bunch of topics. I add one more thing in, and you've got to be able to integrate it to everything else you've already learned. It's tough. Here I've got the function f of x equals x to the fourth times the sine of x. Okay. Let's find the derivative of this. So to find the derivative of f, I'm going to have to use my what rule? Got to use my product rule. So here we go. It is the first times the derivative of the second plus the second times the derivative of the first. I do think that you should clean things up in the sense that you should lead with polynomial terms. If you don't do that, I won't dock you, but it's polite. Questions on that?
We would just leave it at that.
Yep, yep. You could, I mean, yeah, my math, I mean, you could factor stuff out, I don't care, but that's fine. Yep. All right. Here I've got, and I'm sorry, I used the same letter. This confused somebody in my earlier class. I used the same letter here, but this is a brand new function. Every time I say let, I'm redefining the function, even if I've used that f before. So this is a new function here. F of theta is equal to the sine of theta. Okay. Give an equation to the tangent line of f at theta equals pi over 4. Okay. So here we go. Well, we know that the equation of any tangent line looks like y minus f of a is equal to f prime of a times x minus a. So we've got y minus f of pi over 4 is equal to f prime of pi over 4 times x minus pi over 4. Okay.
Wait, a pi over 4, isn't that the maximum, so there's a horizontal tangent?
I think you're thinking pi is over 2. Pi over 4 on my sine function is right about here. And I'm looking for the equation of that line right there. So not a maximum. It is where it's rising the steepest, which is interesting. But it's not a peak or valley of the sine curve. Okay. So if I'm going to use this, I need two things. I need to know what f of pi over 4 is, and I need to know what f prime of pi over 4 is, right? Let's do the easy one first. Oh, and I should use, let me use thetas on these. Just because that's how I gave the problem to you. This is theta, and this is theta. So what is f of pi over 4? Well, that's just the sine of pi over 4. Folks, this should not be an arduous task. I know it probably is for a lot of you, but you got to get fast at it. There's that triangle that gets me to pi over 4. How'd I get there? Same. Let's write it out. Radical 2 over 2, comma radical 2 over 2. Okay. For the sine, which of these two do I want? I want the y value. Of course, if you mess it up, you're home free on this case. Right? But not always. It's the hard part about math, right? Sometimes you can do the wrong stuff and get the right answer. It's still wrong. Okay, now what do we need? Well, we found f of pi over 4, so that step's done right here. Now we need to find f prime of pi over 4. So what is f prime of theta? It's the cosine of theta. Folks, if you haven't caught on to this part yet, let me say it, because I don't think I've said it aloud here. If you want to find f prime of pi over 4, you find f prime of theta first. Then plug in pi over 4. If you plug in pi over 4 first, you got a constant. The derivative of a constant is always 0. Okay? So you always find the derivative first, then evaluate at that point. So it's a two-step process. Okay? Now let's find f prime of pi over 4. Well, that's equal to the cosine of pi over 4. What is the cosine of pi over 4? It's the square root of 2 over 2. Okay? So finally we can give the equation of the tangent line as y minus radical 2 over 2 is equal to radical 2 over 2 times theta minus pi over 4. Okay? Yeah. So I've said I'm always fine with you leaving it in point slope form. My math lab would want you to simplify it. Okay. Trying to get you guys like me more than the computer. We'll see if that works for you in the semester. All right. I'm not going to prove this one. We don't have time. It's very similar to the proof of the sine function. Just the ordering in which you do the limits is a little bit different. But it turns out that when you go to take the derivative of the cosine function, you get what? Negative sine. So close, not quite the sine, but negative the sine. Okay? And sure enough, we can look at that at Desmos real quick if you want. If I take the cosine function, okay, there's the cosine function. Its derivative is the minus sine function, not the sine function. All right. So I'm sorry I'm not going to prove that one for you, but you don't really learn anything new by this proof. So, all right. I can't remember. I wrote these notes. They've been building for 5 years. I don't remember what the hard way is, so I'm going to do it this way instead. Okay. So we're looking at d dx of the tangent function. How do we take the derivative of the tangent function? Folks, in math, you often take 2 steps and then you shortcut it. We found the derivative of the sine function. We found the derivative of the cosine function. Let's not reinvent the wheel here. What could I do with this expression? Yeah, let's rewrite it as the sine of theta over the cosine of theta. Okay. But now to take this derivative, what am I going to have to do? Was there a question?
Well, why is theta in there, not x?
Oh, I don't know. Same answer as you guys. Sorry, that these really they do need to agree. So this is x, this is x, this is x. Yep, great. Thank you. Awesome. Yeah, I mean, look at the structure now. I took this tangent theta. I don't know how to take the derivative of tangent theta. I don't know how to do it. But I can rewrite it as something I do know how to take the derivative of, but I'll have to use the quotient rule here. Okay. All right. Help me out, folks. For the quotient rule, we take the bottom function, cosine of x, times the derivative of the top function. What is the derivative of the sine? Cosine of x. Minus let's see, bottom derivative of the top minus the top, times the derivative of the bottom. This is what we just learned. The derivative of the cosine, be very careful, is the minus sine of x. All over the bottom function squared. Okay. that gives me cosine squared x plus, because of those two negatives, sine squared x all over cosine squared x. Ooh.
1 over cosine.
Can I cancel those two a's?
No.
Oh. I could write it as a over a plus b over a. That's a legal move. And then cancel those two a's. But be careful.
I see. Right. This doesn't
This gives me 1 over the cosine squared of x, right?
Oh, because it's, yeah, it's just the Pythagorean theorem, just looking at one, right?
Yeah, what is cosine squared plus sine squared? Yeah, it's 1. Sir? Yeah, I think I'm okay because of these two negatives. Yep. What is 1 over the cosine squared? It's the secant squared of x. So the derivative of the tangent is the secant squared of x.
Are we gonna have this derivative
It's
for
like
the
secant.
test?
No. But there's enough steps in here that I've shown you that I might, once the derivative of f shows up, I'll want you to replace it with f prime of x. Or once sine of x over x shows up as the limit as x goes to 0, you need to know that that's 1. So I can ask you stuff like that. But I won't ask you to regurgitate one of these proofs.
Does secant go with cosine and cosecant goes with sine?
Yeah.
I don't know what you mean by goes with. I mean, they all kind of go together. But the reciprocal of the secant, so the secant of theta is equal to 1 over the cosine of theta, and the cosecant of theta is 1 over the sine of theta.
That's what I was
Yep.
asking. Yeah.
Yeah.
So if you broke those out, if you still went that far, then it would be.
Yeah, you could have done that.
Cosine squared plus sine squared over cosine squared, so it's 1 plus tangent squared, which is equal to.
Secant squared. Yep. There's many ways to get there. Yep. Yeah. Great. All right, folks. Here they are. Okay. Memorize, yes. Memorize them all. But I had some people say, "Oh, you memorize them at least till you get to the test." No. These you should be able to do without thinking. Those 4. Like somebody should be able to shake you from the dead of sleep and say, "What is the derivative of the secant of x?" And you say, "Secant x tangent x." Let me go back to sleep. Okay? You need to know them that well. Okay? These other two, go ahead and there's something that you right before the test, right when I hand out the test, you write them at the top. Okay, in case I just happen to ask them, but I probably won't.
The cotangent one, you could kind of argue that you should know too, since it's.
Yeah, I've arranged them in such a way that you can, well, not me, everybody does. You can sort of see the patterns going on here. Okay? All right. Okay, folks, let's do 12a. Let's do 12a. I'm just going to work it for you. The derivative of x is equal to the bottom times the derivative of the top. What is the derivative of the secant?
Secant x tangent x.
It's like you got it right in front of you. Okay? Minus
1 plus
the bottom,
the derivative.
the derivative of the bottom, which is what?
1 plus secant squared x.
Careful. The derivative of 1 is
Oh,
0 plus secant squared x times the top. You don't need that 0. All over the bottom squared. Okay? This is definitely one where I'd say do not worry about simplifying. Yep, you'll have to.
Are they asking this hard question on math lab?
I don't know. I don't think it's set that.
You're right. I mean, unless you had to keep going and
Yeah. So yeah, cleaning it up might be yeah.
cleaning up it would be a little tricky because
Yep.
you'd have like 1 secant. It's all good. It's all good.
Okay.
Ain't no thing.
Folks, here's you get some chance to practice these. Okay. Please take a look at them. I do want to do. I want to show you this one real quick. Okay. What is the derivative of the sine of x?
Cosine of x.
What is the what is the second derivative of the sine of x? Oops, I wrote that wrong. Sorry, folks. So the second derivative of the sine of x is the derivative of the cosine, and what is the derivative of the cosine? Negative sine of x. What is the derivative of minus the sine of x? Yeah. What happens to that minus sign? It tags along for the ride. So we'd have minus cosine. So what is the fourth derivative? Yeah, so I'll write it out here. The minus comes along for the ride. What's the derivative of the cosine? It's minus sine, but those two cancel out to give you just the sine of x. Okay? So this is a song that has 4 verses and you start over, right? Okay? So what is the fifth derivative? Okay. What is the 35th derivative? This is gimmicky, folks. This is gimmicky, but I do need to show it to you. Take 35. How many verses did we say were in the song? 4. Take 35 divided by the number of verses. Okay? So 4 goes into 35. Help me out, folks. 8 times 32, remainder of 3. This means that I'm going to go through the song 8 times completely, and then 3 more verses. So what was the 3 more verses gonna? What will that work out to be? Negative cosine of x. Okay. Everyone okay with that? You saw the same versus trick when you did like. This is a silly college algebra problem. What's I to the 361st power? You know, and you divide by the number of verses, and then you count the remainder.
This doesn't have any relationship to the fact that these have 4.
No. No, that's not true. There is a relationship, but it's more subtle than that.
Okay.
Yeah.
There's got to be something.
Okay, folks, I do want to show you number 16 here. Okay. I'm not going to show you all of these, but all of these proofs, or all of these limits, rely upon the fact that we already said the sine of x divided by x is 1, and then we use our identities to help out. Okay? So notice that I could rewrite this as the limit, as x approaches 0, of the sine of 2x plus x over x. And now I can use my sum angle property. This gives me the limit as x approaches 0 of the sine of 2x times the cosine of x plus the sine of x times the cosine of 2x all over x. Okay. Now what can I do? Well, I can rewrite this as the limit as x approaches 0 of the sine of 2x times the cosine of x over x plus the limit as x approaches 0 of the sine of x times the cosine of 2x over x. I can do that, but I still have one more. So this one has a 2x in it, and it needs to be broken down one more time using the sum identity one more time. Okay? So that's the limit as x approaches 0 of the sine of x times the sine of x. That's going to be sine squared x plus cosine. Oh, that's a lie. I'm sorry. This is sine of x times the cosine of x plus the sine of x, cosine of x, cosine of x, all over x. That's the first one. Plus, I'll break this limit up as sine of x over x times the limit as x approaches 0 of the cosine of 2x. Folks, I'm going to stop there. Yes, it can, but it could also be evaluated through direct substitution, right?
That's cosine of 0.
Because it would just be the cosine of 0, which is 1. No problem. I'll stop there, but do you see what the idea is? I'm basically using my trig identities, and I did that really fast, but I'm breaking it down to things I can either evaluate through direct substitution or this identity right here, which is 1. So you use your trig identities in clever ways to just stagger this down. Okay? Certainly this would have been excruciatingly mean if I had put 5x over x, okay? Because you have to work through that property several times. Yeah, Maria.
Sorry, I got lost. Where did the sine 2x times cosine x go?
So this sine 2x, so here is the cosine of x right there. And then I broke up this sine 2x using a similar property to what I did right here. So I thought of the sine 2x as the sine of x plus x. And then I used the sum angle on that. So the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first.
I don't like that. He's trying to